Oh, geez, here we go. All right. So let's take a look at the homework here from section 5. Now the big thing from section 5 is this idea of zooming, which for us, unless they specifically said, I said this yesterday, but I don't know if it sunk in completely, but unless they say specifically, find a window, on your calculator, zoom in until the curve is straight, kind of a thing. But the idea behind doing that, right, is to realize that we're trying to find the slope of a curve. We're trying to find the slope, like these little black tangent lines. You've got the e to the x curve. We're trying to find the slope of a curve, but the slope can really only be found, at least for us right now, by doing 2 points, right? I mean, that's really the only way we know about doing a slope. And so the slope of a curve really means the slope of the tangent line at that point on the curve, but then that only point we know is that point where it touches. And so what we're saying is if you zoom in, zoom in, zoom in, zoom in, no matter how curved the thing is, if you zoom in at a point, eventually you can get in there far enough where it looks just straight. It looks like the little black piece there, right? It looks like a straight line. And so the idea is you could just take 2 points on that and do a slope calculation. And that would be the slope of that black line. So really, so that's the idea, to visually understand that. But as far as, unless they say in the problem, they want you to zoom in, find the window, that kind of thing, you don't have to physically on your calculator zoom in, zoom in, zoom in. It just means pick 2 points really close to wherever they're wanting you to do the slope and do a slope calculation. That's what it means. And if you're on a table, if you're doing a table of values, pick the closest 2 points you can to where you're trying to do the slope. Okay? So I wanted to make a comment about this. I think I maybe talked about it the other day, but so if you think, or yesterday, but if you think about this zooming in, if you took the V graph and notice the scale here, -1 to 1, and you zoomed in, and notice the scale over here, it looks the same. No amount of zooming in is going to make that look straight. So the idea there is that when you have what we'll just call a sharp point on the graph, a sudden change in direction, the slope there is undefined. The slope does not exist. We do not call this a zero slope right there, like we would at a nice smooth local minimum. This is still a local minimum, but the slope there is undefined. So anytime we have a sharp point like that, the slope is undefined. Now another time when the slope is undefined, and I think actually it did come up in one of the homework problems, but another time if you would graph x to the 1/3, or cube root of x, here's what cube root of x looks like. It comes up like this, and then it kind of goes like this, and then it goes like that. The tangent line right there at the origin is vertical. It's got a vertical tangent line. And so anytime the tangent line on a curve is vertical, obviously that slope is undefined as well. Okay? So those are the two big times where slope of a function is undefined, is when it's a sharp point and when it's a vertical tangent line. Okay? So just for future references as we get into these kind of problems. Okay? Are there any questions before number 25 on the homework? Because I want to talk about 25, I want to talk about 30, I want to talk about 38. So did anybody have anything before that they were concerned about? Okay. All right. So 25, because we do have quite a bit of other stuff to do today, and so this wasn't a real long assignment. So here's 25. So what you were supposed to do on 25, and they said in part B, it said, did your answer support what was stated back in that example 6 or whatever in the book. So what they wanted you to do, here was the e to the x graph. They wanted you to find f prime of 0.5 by zooming. So to me that means find a point, a couple points really close to 0.5. So I did 0.501 and 0.499. You could have done something different. We were talking this morning, somebody did 0.6 and 0.4, which is fine, but I'm like, if you can pick points close to 0.5, why not get a little closer, right? I mean, I can put a whole bunch of zeros and get really close, but then at some point it's too many digits. But to me, that's pretty good right there. Now, let's talk about the calculator. So Akshay, you're up. So how could we do this on our calculator? So just go to your scratch pad. Let me show you all the various ways you could use your calculator to make this calculation. Okay? And I can see what he's already done there. That was problem 38, I think, right, with the sign and stuff. Okay, so what are the various ways we could do this calculation of e to the 0.501? Well, one would be like what he just did, right? So what I would do, and I have it written up here earlier. Let me go back, to this for a second. So notice I like to write it with F notation always. I like to use function notation for my slope, f of b minus f of a. I always like to write this first, because when it's a simple function like this, yeah, that's easy. But if this was a complicated function, like e to the x plus sine of 2x minus, then all of a sudden it gets kind of confusing to put a 0.501 in there, every one of those places, right? So I like to just write the F notation. That, to me, is easy. And if this was a complicated function, let me show you what I would do to take advantage of the power of my calculator. So one way would be to just hit Control Divide, and get a fraction. Now do e to the 0.501 minus, e to the 0.499 over, and then 0.501 minus 0.499. Now, so that would do one, and you can even just do the top first, and then do the bottom, and then divide, whatever. So it'd be a lot different ways. So hit enter, and you get that. Okay, now, but if it was a big messy function, and I had to plug numbers into it, right, f of this, f of that, whatever, then I would actually define my function to be that. So do this. So go to menu and actions, and then number 1, define, and then type f parentheses x, and you can actually define your function right here on your screen, and then equals e to the x, and hit enter. And now do your Control Divide for your fraction. Yeah. When you put that 0.501 in. Go ahead and type now. Go ahead and type f of 0.501. And the only reason I know that is because, see, the E here is like a bold face, kind of a darker thing. I should have said that. That was, I don't even know why I wouldn't mention that. The E on the keyboard is different than the E over here, yeah. Over on this one. Yeah. So if that was that may have been happening to some of the rest of you too. I didn't know. And then, oh, I'm sorry. Do this right here. So go back up here, Akshay. So minus f of 0.499 over, and then 0.501 minus 0.499. And now if your function was this big complicated thing, with multiple pieces and parts to it and stuff, then you would still have this nice easy thing to type in. So defining your function is something. The other thing you can do is put it into your graph screen, because that's what's that called, f1 of x, right? So if you would have typed this into your graph screen under f1 of x, then that's defined as f1. So back on your calculator screen, you could use f1 parentheses x as your function. You could use g of x, h of x, whatever you want, right? So anyway, so those are some things, some little tricks of typing some things in on your calculator screen. All right, now back to the question. So that means that the slope at 0.5, so right here, oh wait, no, right here, at 0.5, the slope is about 1.6. Okay, about 1.6, which seems reasonable because the y's here go up by 2's. So if I go over 1, it looks like I go up a little more than half of one of those. So 1.6 seems reasonable. So I'm getting about 1.6, what was that? 487. Now, what was their claim? Let's go to part B now. What was their claim in that example about the e to the x graph? That the outputs of f of x were equal to the outputs of f prime. That is, think about this. And people often say, what's so special about e? Why do we have this number 2.718? Why natural log? What's going on? Well, this is just one of the cool things we'll see about e that makes it a special number. And that is that it is the only function of all the functions. It's the only function other than a simple function like y equals 0 or something like that. But it's the only function where its outputs are the same as the slopes at that point. In other words, if we go back, if Akshay will do this for us, if you will put in f of 0.5 right now, because remember, this number here is our slope at 0.5. Put in f of 0.5 and hit enter. That is the y value at 0.5. And look how close they are. Now, why aren't they exactly alike? What's that? On with our what? Yeah, right here. This is just an approximation of the slope, right? We just picked two really close points. It's not exactly the slope. It's just an approximation. But you can tell it agrees out to quite a few decimal places, right? Every point on the e to the x graph, that is true. Amazing. The y value on the e to the x graph is exactly the same as the slope at that point. And it's the only function that has that. If you do 2 to the x or 3 to the x or something, they're close, but they're not the same. They're not the same. So that is a cool thing about e to the x. And that's what they were getting at on that problem. Okay, let's go to number 30. Okay, and they ask you a couple questions about square root of x. Now, here's the function square root of x. This is a function we should memorize. Okay, we should memorize its picture. Now, what is that? What shape is that? What shape is that? Starts with a P. It's the top half of a sideways parabola is what it is. Because y equals square root of x. Where does that come from? If you square both sides, you get x equals y squared. Remember when you studied parabolas last year? The ones where the y is squared, those are sideways parabolas. Of course, it wouldn't pass the vertical line test if we had both halves, right? So if you square root both sides of that, of a sideways parabola, you get plus or minus square root of x. Kind of like the top and bottom half of a circle, right? Plus or minus square root of x is the top, is both parts of the parabola. Y equals square root of x is just the top half of the parabola. If we had negative square root of x, it would be bottom half. That's probably a good point for me to talk about another one of my little pet peeves. That, not pet peeves, but it's one of those things that we don't understand real well and we struggle with sometimes. If I ask you, what's the square root of 9? And understand that many of you are gonna say it wrong, and don't feel bad because everybody does. No, it's not plus or minus 3. It's positive 3. If I ask you to solve x squared equals 9, the answer is plus or minus 3. Those are two different things, okay? When we do the square root of both sides of an equation, we have to do the plus or minus because x could be positive or negative here, and solve this equation because it works. Put a 3 in, it works. Put a negative 3 in, it works. It's plus or minus 3. So when you do an equation where you're solving and square rooting both sides, you have to do this plus minus. Now, based on things that are happening in the problem, you may get to eliminate either the plus or the minus, whatever, kind of like we did with the top, bottom half of the circle. But when you're asked what's the square root of 9, that is just 3. If you wanted the negative square root, there would be a negative in front of that. Those are two different functions. So the square root as a function is the positive square root of that. Okay, so those are two different questions, so we want to be careful with that. So square root of 9, the answer is 3. Solve this equation, the answer is plus or minus 3. So subtle little difference there, but it is important. So anyway, the square root function is just positive outputs. Just positive output. You put a 9 into this, you get out a 3. Okay, so this is a parabola, top half of the parabola. So what is the slope at 0? They ask. Yeah, that's right. If you think of it as a parabola, wouldn't the tangent line right there be vertical? Yes, it would. Just like on a normal parabola, this kind of parabola, the slope is 0, right? So right here, so we were just talking about that. What are some of the places where slope is undefined? Well, one of those is a vertical tangent. So right here, now my picture is not very good, but we would have a vertical tangent right there. So this is undefined. What about f prime and negative 1? Undefined because, yeah, you're not... there's no point. The function is undefined at negative 1. So if there's no point on the function, there can't be a slope at that point, right? I mean, so it's not in the domain of the square root function, so there can't be a slope there. So I guess that'd be another time the derivative is undefined, is if the original function is not defined there. Okay, so a couple of interesting facts about that type of function. Okay, now let's talk about sine. This is a really good problem here, number 38. So we did this one in class yesterday, right? Pi 6 was like, what was it, 0.5 something? I can't remember. Help me out. 0.5235 something, and we picked points on both sides, and we did this. Okay, so then they want us to find f prime at 0. Okay, so actually, let's go back to you, and now let's define, here, arrow up here real quick. You can shortcut some of this. Hit escape. Arrow up to this. Hit enter. Okay, now delete that and put sine x there. I get lazy sometimes too, and I want to. So there's little tricks you can do on your calculator to make things faster. Okay, there you go. So now let's do some points here. So so at 0, I picked something on both sides. So I got negative 0.001 and 0.001. So we're going to do, So we're going to do the sine there. So go ahead and do that. Nice thing is once we get this up here, well, okay, that's fine. You can do sine. When we defined it as f, I thought we'd just use f, but that's fine. It'd be faster to use f. You can do it on the next one. Negative 0.0, let's do 2 zeros and a 1. There you go. Minus, and then f of, and the nice thing is we can go up and grab this and just change our numbers, right? Because it's still the sine function every time. So we don't always have to retype everything. Okay, what would you call that? 1. So it looks like the sine graph at 0 has a slope of 1. Seems reasonable. 45 degrees. I would say that's probably 1. Okay? And then we were supposed to do what? F prime at, we did pi over 6 already. Pi fourths. What's pi fourths as a decimal? 0.7. 0.785 what? 3. So let's do f of 0.786 minus f of 0.785. So that'd be on both sides of that. And then 0.786 minus 0.785. Let's do that. 0.707. All right, and then we were supposed to do what? Pi thirds? And that's about what? 1 point, how much? 7, give me 0.047 something. So let's go f of 1.047. What'd you say it was? We'll go 0.047, that'll be fine, and then minus f of 1.048. Right? Over 1.047 minus 1.048. Okay? So we're just picking a point, that pi thirds, we're picking a point and we're plugging it into the f graph, right? But what we're finding is f prime, because f prime is slope. We're doing a slope calculation right around pi thirds, right around 1 point whatever. We're doing a slope calculation right there with 2 points really close, and we're getting these slopes on here. So pi thirds, so we're right in here somewhere. So we were 0.7, we were here, we got that, and we got that. What are we getting on that one? 0.5. Okay, I don't believe you. We better show it. Oh, yeah, he's right. All right, 0.5. All right, so we got that, and then there's another one. Pi halves. Let's do that one. And pi halves is what? 1 point. That's 1.57. What? 1.570. Okay, so let's do f of 1.570 minus f of 1.571 over 1.570 minus 1.571. So those are two pretty close points. And that'd be the slope up here. And geez, while he's doing it, we should get what? Yeah, we should get 0, right? Because just looking at the sine graph, I can tell up there we're going to have that. Probably going to be a scientific notation thing, right? E to the -4, so 0.000 something. So pretty close to 0. All right. And then, now what did it say on the next one? Using symmetry, or yeah, in that part.
I use symmetry on the sine function in your answers for part A to estimate f prime of 2 pi thirds.
Okay, so here would be pi thirds about here. And here would be pi fourths about here. And here would be pi sixths about here. So using symmetry, what they mean is, wouldn't the slope be about the same over here? Except negative. So this is pi 6. This would be what? 5 pi 6? So 5 pi 6 ought to be a slope of negative 0.866. Does that make sense? And pi fourths over here would be, so at 5 pi fourths, looks like we'd have about negative 0.707 slope. And at pi thirds, so 2 pi thirds would be right there. So 2 pi thirds looks like it would be about negative 0.5 slope. And then pi halves, this slope would be the same, or no, I'm sorry, 0. We had 1. So I'm guessing here at pi, where am I at here? 0 right here. So at pi, we should be getting a slope of negative 1, right? So that's what it meant by using symmetry. Then what they want you to do? F prime points. Did you get it graphed? Was it really cool? What was it? That's what we're supposed to go. Look at these values. I mean, did that look familiar at all? 0.866? What's 0.866? Root 3 over 2. What's 0.707? Radical 2 over 2. Right? 1/2. Right? These slopes we were getting are values we get out of sine and cosine. Right? Now, of course, sine of pi 6 is 1/2. But the slope at pi 6 was root 3 over 2, which is the cosine of pi 6. I don't know what it is about that, but that's just amazing. The e to the x is cool too. The slopes of the e to the x graph are exactly the same as the outputs at that point. That's really cool to me. But this is even cooler. The slopes on the sine graph are the outputs of the cosine graph. Unbelievable. So at 0, we get, what did we say? At 0, we got a slope of 1. So I meant to do this in red. So in red now we're graphing the f prime graph. So the slope at 0 is 1. The slope at pi 6 is about 0.86 something, which is in here. The slope at pi fourths is 0.7, so it's kind of coming down. The slope at pi thirds is 0.5, so it's here. The slope at pi halves is 0, so we're here. So it's coming down, and it's doing that. And then at, what did we say, 5 pi 6, that was negative, no. What would come next? 2 pi thirds would come next. That's negative 0.5. And then what would come next would be 5 pi fourths would be negative 0.7, so it's down a little farther. And then at 5 pi 6, it's negative 0.8. And then at pi, where was pi? Right there, pi, it's down at negative 1. Sure enough, they come down here and do this, and then it would repeat again, and da-da-da. So you have just learned your first 2 derivative formulas. If f of x is equal to e to the x, then f prime of x is equal to e to the x. And the second one you just learned is that if f of x is sine x, then f prime of x is cosine of x. Or what we say there is the derivative of sine x is cosine x. The derivative of e to the x is e to the x. And we are going to do that more and more. We're going to get into chapter 2 and do that. Actually, chapter 2 and 3 is where that's really a big deal. So for now, it's just kind of, wow, that's really cool. But later on, we're going to get into, I guess you'd call them slope formulas, right? It's nice. If we have an equation of a function, it'd be nice if we had an equation of its derivative. Because then we could just plug numbers into that to get the slope. We wouldn't have to do this thing with 2 points all the time, right? That would be a pain if we had to do this all year long. Right? We always have to pick 2 points really close together and do it. Well, we're not going to have to do that all year long, right? We're going to come up with these formulas.
So then would the derivative of the cosine graph be the sine graph?
That's a great question. We can investigate. It definitely seems to make sense that there's some connection. So let's think about it. Here's the cosine graph. Okay? What's the slope at the start? So let's start plotting it. What's the slope here early? Negative. And getting, or we've been talking about that, it's negative slope, but getting more negative, steeper, so it's like -1, -2, -3. Well, it's not, but it's that. It's getting negative and more negative until where? Till the inflection point. Now it's negative slope, but getting not positive, but less negative, right? It's getting back towards what slope here? 0. So right here we get a 0 slope. So it's going to come down. Looks like it's going to come down and then come back up. And then, so it looks to me like it's what? That's not sine. Negative sine. Negative sine. So it turns out the derivative, so you're right. Well, we just got our third function. The derivative, so if the f is cosine, the derivative of cosine is negative sine. Now we'll end up with a whole kind of page full of rules and derivative formulas that we'll work on and memorize and everything, so forth. But there's a couple of them right there, absolutely. Okay, yeah. Go. All right. So, good question. But yeah, it's easy to just notice there with that one we could do that. All right. So that's why I like that problem. 38 is a really cool problem because of that. It's something we actually were going to do later when we got into some more trick stuff. But since we're calculating these slopes, I thought it was a good time. That's why I added that on there today. Okay. So that's enough of that. So this whole idea of slope, this whole idea of f prime and notation, whatever, that was section 1.4, section 5, just like, okay, how would we calculate slopes? And that's all we've got right now. We know we're headed towards, we're going to get some formulas and stuff like that, but we got a lot to do between now and developing these other formulas, but there are just a couple of them, so you can kind of see what's going to happen. So let's go ahead and get started with section 6 here today, and we're going to just continue to investigate the ramifications of this function called f prime. What is this about? We got the speed limit law, which kind of says, hey, if you know something about f prime, if you know the slope, that tells you something about f, like how much it's rising, how fast it's going up, or whatever. So we have those speed limit law problems. So we're going to kind of continue in that vein. What does f prime tell us about f? That's really that's really what this section is about. What does f prime tell us about f? Because what we're going to find out is that if I have a function f, but let's get into the real world. So in business, I have a function that's profit. And I want to find the maximum profit. I want to find when that function is at its peak. Well, how would I find that? Well, it turns out the slope is going to have something to do with that. So what f prime can tell us, the derivative can tell us about that function, could be useful in solving problems. Okay, so that's just a thought of why this might be important. So what does f prime tell us about f? So if you would pull up that derivative grapher document, and let's see, actually you can be done for now. Thank you. But if you would pull up, oops, that's the wrong one, the derivative grapher document, and we were over here on page 1.4, I think, the other day. All right, so what we're going to do is over the course of a couple of days here, we're going to answer this question, what does f prime tell us about f? So today we're going to start by just throwing stuff out, kind of in random order and just throwing some things out there. You don't need to write them down, or you can, whatever. And then you're going to have some homework questions where you have to think about these things and so forth, and it'll seem a little jumbled, and that's natural. And then on Monday, we're going to try to organize it a little better, okay? Try to organize all these things that f prime tells us about f. And then just keep working on getting that more organized as we go through the week. Okay, so here's f prime in red. Here's f in red. Here's f prime in blue. So f up here, f prime, you can see it right off to the side here. So what I want to do, and I want to be using words like positive, negative, zero, increasing, decreasing, local max min, inflection point, concave up, concave down. Those are the things we're talking about. So when we say, what does f prime tell us about f? Oh, f's increasing. Oh, f has a local max. Oh, f's concave up. Those kind of things, okay? All right, so we're going to throw them out here in kind of random order. So I'm going to go back here. Somebody tell me something. Now we said, what does f prime tell us about f? So we're looking at the blue graph right now. So we're looking first at the blue graph. So tell me something about where I'm at on the blue graph. Tell me something about f prime right now. F prime is what right now? What's that? F prime. Is that a local maximum right now? I'm talking about this point right here. F prime is what right there? There'll be several things you could say. Positive. F prime is positive. When I say F prime, I'm talking about the Y value now, right? I'm talking about the output, right? Okay. Right there, the Y value is positive. Does that correlate to anything on the red graph? That means the slope of the red graph is positive, which to us means what's happening if slope is positive. Increasing. Going up is increasing. Okay, so let me say it again. So let's say it again. So f prime is positive, means f is increasing. Now let's see if that holds true all the time. So let's slide this all the while that f prime is positive. So f prime is positive here, right? F prime's positive here. F is still increasing up there, right? Let's keep sliding it. F prime's positive, F prime's positive. F, meanwhile, is increasing this whole time. And all of a sudden, F prime quits being positive. And does F quit increasing? Yeah, I'd say that was a good comment. Now, what's F prime here? Negative. What's F doing? Decreasing. Oh, it makes sense because F prime is slope, and so if the slope's negative, it means the graph's going down. So there's a couple things we got, right? If F prime is negative, F is decreasing. If F prime switches back to positive right here, right, it's above the x-axis, then F is increasing. Okay, so there's a couple times. Remember, what's our theme here? What does F prime tell us about F? There's a couple of things. All right, what else? What else is the blue graph doing right here? Isn't it going down? The blue graph is going down there, right? Does that tell us anything about F? So the slope is getting less. The slope is decreasing, right? Because if F prime is slopes, the y values are the slopes. So if the y values are decreasing, which they are all the way here, then what does that tell you about F? Yeah, I know the slopes are decreasing, but let's use another term. Is that concavity? So the fact that the blue graph is going down, I would agree that the red graph's concave down. Now, what about when we cross the x-axis? Does that matter? Okay, now, is the blue graph still decreasing? Is the red graph still concave down? So let me ask that again. Does it matter that I cross the x-axis? Not for the statement that if F prime is decreasing, F seems to be concave down. Now, it did go from this to this, right? But let's talk about that. Is that still slopes decreasing? Here you said they were getting less steep, right? That's the slopes are decreasing. Now over here, are the slopes decreasing here? Give me some numbers. What are the slopes? 0. -1. -2. Is that decreasing? That's decreasing. Oh, remember that thing I said about positive and getting less positive, that kind of stuff? Decreasing, to me, there's two ways to decrease. Here it's positive but getting less positive, and then when you cross here, they're negative but getting more negative, right? Those are both decreasing situations, right? But either way, isn't that concave down? I think you're right. And then when this graph stops decreasing, doesn't the red graph switch to concave up? Isn't that an inflection point right there? Interesting. Switches to concave up. So there we go. So F prime tells us not only when the red graph was going up or going down, the blue graph also seems to tell us when the red graph is concave up or concave down, right? What about local maxes and mins? Here's a local max or min on F.
Across the x-axis.
Ah, look at that. Now, that's a local max. Here's a local min. It's on 0 again, right? So it looks like it's both local max and local min is when F prime crosses the x-axis, when F prime is 0. Interesting. What about the inflection point? That was another one we had. The inflection point on F corresponds to a local max or min on F prime. So you can start to see how this gets a little confusing. Okay, the local max min on this was what? So we'll organize that, right? We'll continue to organize that. But right now, I purposely am not going to organize it more for you because I want you to think through it. I want you to think, you know, if we get some problems and we say, well, hey, F prime is positive here, what's that tell you about F? And I want you to think, oh, wait, I don't want you to just look at a chart and just, right? I want you to understand it. So I want you to think, oh, when F prime is positive, what's that mean? What's that mean if F prime is positive? It means the slopes are positive. What's that mean to a graph if its slopes are positive? Oh, it's going up. It's increasing. See, I want you to think about this, right? Or like we said, F prime is decreasing. F prime is decreasing. Oh, F prime means slope. Slope is decreasing. What's it mean for a slope to decrease? Well, it means the slope is 5, then 4, then 3, then 2. What's that mean? That's curving down. That's concave down, right? So I want you to go through that process of thinking it through, right? And it's going to come faster for some than others, right? And that's normal. All right. And then as we do that, and then we'll kind of organize those things a little bit, and then there'll be some memorization involved a little bit, but hopefully you'll just work with it and understand it enough that the memorizing it just comes pretty naturally. Okay. So here's what we're going to do. We're going to do this. You can get with a partner or groups of more than 1 or 2 or 3 or 4. I guess a group of one's not really a group, is it? Get into groups of 1 and go through this. So the document you have is, so this would be the first derivative test document. Okay? And so what we're going to do is you're going to read through this, you're going to fill in these blanks in these boxes, and you're going to kind of come to, hopefully, a little bit of a discovery. We've kind of hinted at it up here already. And you're going to kind of come to a little bit of a discovery of something that's called the first derivative test, okay? And so we'll spend some time working on this, and then hopefully by about 20 after or so we're getting done maybe, and then we can talk about it, and then we'll talk about the homework, okay? All right, so go ahead and get to work on this. So you just follow the directions. You'll do some things on the document as you answer these questions. Now, Emily, I'm going to pause it. So when we get back together, remind me to start. Hey, to make sure everybody's on the same page here. So you had a critical point at 3 on that first one, or was that on the second one?
No, it's the first one.
First one, and that was a local minimum. And the interval where the slope was positive.
3 infinity.
So your answers are looking something like this, right? That kind of thing. And so what they're saying is that on this findings here, they're saying something about this is what's determining this. I think that's the key, what you're looking for. Okay? This seems to have been negative before 3, right? The slope was negative before 3, and it was positive after 3. And does that have something to do with the fact that was a local minimum? Right? See what we're saying? And so on the back, when you get to that, they talk about sign change. Well, what they mean is like from positive to negative or from negative to positive. So that's kind of what you were seeing here, right? Okay, so you're kind of on track with what's going on there. All right, back to work.
Changes.
All right, so let's look at this thing, and it's got all the different stuff I have up here on the board, right? It's got some sharp points. So these are local maxes and mins. This is a vertical tangent. This we call a flat spot. For lack of a better name, some books call it a terrace point. But I'm like, okay, terrace point, I guess we could call it that. Flat spot. It's definitely where the slope is 0, but it's not a local max or min. Okay? Now, if we wanted to maybe give a couple of definitions that might be worth writing down, we talked about critical point there at the beginning of this worksheet. So critical point is a point on F. So that was the first part, what they said in the worksheet. It has to be defined. It has to be a point on F. You can't have a critical point of F if there's no point of F. So the critical point of F is a point on F when F prime is either 0 or it's undefined. Either 0 or it's undefined. So all of these up here on the board, and I'm sorry for those listening to the video, you can't see those, but all the ones on the board here are critical points. And the ones, and then there's this other thing in this section 6 that they define called a stationary point. A stationary point is like a subset of critical points. Stationary point is just when F prime is 0. So you would take out the sharp points. So if you're listening to the video, I'm circling on the board right now. Those would be stationary points because those, the derivative is 0. The other 3, the derivative is undefined. Okay? I guess we could put those up here. So stationary point, right? Those are stationary points. Critical points would be those and those. So the derivative is undefined there, derivative 0 there. All 6 of those would be critical points. Just these down here would be stationary points. Okay, so back to this worksheet then. So the idea is that we're talking about these sign changes. So at -8, so it would be something like this. So at -8, and I can do this pretty quick because I can just drag this real quick. So what you guys were doing, you're looking at this slope right here. So here's a local max, and the slope goes what? It's positive, then it's negative. So a positive to negative slope change seems to be a local max. Oh yeah, the graph's going up, then it's going down. Duh, local max. Then here we got a local min. What's the slope? It's negative, then it's positive. Oh yeah, that seems reasonable. Negative, then positive, that's a local minimum. Okay, that happened not only there, but it happens over here as well at this local minimum. Negative slope switches to positive slope. Local minimum. Now what about these weird ones? Positive slope, and then what happens? Stays positive. Right? Okay? So positive slope, 0, then stays positive. So it's a stationary point, but it's not a local minimum or a local maximum. Here we have a local maximum. We got positive slope, switches to negative slope. Positive to negative switch is a local maximum. Here we have a critical point here where it's a negative slope and undefined and then stays negative. No sign change. Now, let me go back to this picture then. And so we're talking about a sign change of the slope, right? F prime is the slope. So now imagine, and in your homework there'll be a few problems like this. Now imagine we're not looking at the F graph like we were here, but we're looking at the F prime graph. So here is a local max right here, right? Look at the slope. It's what? Positive switching to negative at this local max. Positive slope switching to negative. Look at the blue graph. Positive y value switching to negative y values. That makes sense? Remember earlier we said, hey, the local max seems to be where this crosses. But a line or a graph can cross 2 different ways, can it? It can go from positive to negative. See that switch? Remember, these y values are the slopes of this. So positive slope switching to negative slope. That's a local max. Go over here. What do you got? Negative y values switching to positive y values. Again, where it crosses is a local minimum because that's where the slope is 0. The slope is 0 at a local minimum, but it crosses from negative to positive. Now, I just said it, and I'm going to really try not to and be careful. I just said the word it. We got to really be careful here. I said it crosses it. It has a local maximum. We got to be careful. We're talking about F. We're talking about F prime. So really be careful about those. What is that? A pronoun? No.
Yeah.
Is that a pronoun?
Yeah.
My English isn't good, but we want to say when F prime goes from negative to positive, then F goes from decreasing to increasing, and therefore it's a local minimum. That is the gist of what you just discovered on that worksheet. It is called the first derivative test. Test for what? It's a test for local max and min. A test for local max and min. It says that if the derivative is 0 or if the derivative is undefined, you might have a local max or min. How do we test for it? We check what's happening to the slope. We check for a sign change on the slope. If the slope's going positive to negative, we got a local max. If the slope's going negative to positive, we got a local min. If the slope's not changing sign, what do we got? Neither one. Neither one. That's what was happening on your worksheet there. Okay? All right. We will be continuing to go over this over a number of days. Okay? So your assignment is the next line, which is 1.6 day 1. 1.6 day 1. It says the first derivative activity, which is that worksheet, which is probably pretty much finished. And then a number of problems, not very many. Okay? So do those and go back and look in the section and read some of that whatever and really think about what it is we've talked about as it applies to these problems. Okay? And then we'll come back and jump into it some more on Monday. Okay? See, I just felt